Thank you, Chris. Well, good morning. So as Chris mentioned, I've been, and as many of you may know, I've been on the faculty at Cal Poly for about 11 years, and I am no longer on the faculty at Cal Poly. I left that and am now completely full-time with Uber. Okay, belt and suspenders. But even though I'm no longer a professor, a friend of mine last week down at SciTech made the comment, once a professor, always a professor. So I didn't realize I had that in common with the Marine Corps. But if you'll indulge me in a little bit of a diversion before I get really down to the point, I think one thing that hasn't been talked about yet is what do we actually mean by transformative? And I think this group, really already knows this answer, and maybe we should have had this discussion at the beginning of the week, but I think it's worth at least talking about that a little bit. So, what is transformative flight? And, there's certain things that it's not. But what I really think that transformational flight is the use of flight to accomplish missions that were not previously possible. And I think this is important for us to talk about because as engineers, we tend to examine the systems we're considering designing with respect to the systems that we're most familiar with. We look at things in the light of things that already exist. And that's not fair and not appropriate when we're looking at transformational things. So this is really an exercise for anybody who's, and again, we're kind of in the True Believers Club right now, so I'm preaching to the choir. But for anybody who's not in the True Believers Club, I want to take a moment just to think about transformational. And I'm going to start with a very different mission, right? An aero reconnaissance, a photography type mission. And I want to show a bunch of vehicles that have done this throughout history. And I think this is fun. There's a pretty famous photo up here in the upper left-hand corner that I'm showing. Who's seen this picture before? Maybe it's not that famous. This is actually a Civil War aero reconnaissance platform. Okay, they would put a soldier in a basket, send him up underneath a balloon with a pad of paper and a pencil and a string. And we would make observations and drop that piece of paper down to the ground level and report the observations. Part of this is terrifying. Those two boxes to the left, hydrogen generators in the battlefield, in the Civil War, pulled by horses. Right? This is quite a dichotomy. There was some innovation that went on because at first they went up with a single tether and the observer was spinning around and often made observations of his own forces instead of the other forces. So innovation, 2 wires for a tether. Right? So that's where observation starts. And I think that some of these vehicles you might consider transformational because obviously adding a Mach 3 capability to aerial observation added a level of survivability that transformed the way it could be used. But in essence, it's still doing the same mission. And having a 30-hour endurance of an unmanned platform to go and do this is transformational, but at the same time, it's still doing largely the same mission. So part of my point here is there are shades of gray in transformational. It's not all completely different. Anybody wonder why there's a fighter airplane down in the bottom right-hand corner? Yeah, that's not a P-51. That's an F-6, right? So this is a aerial reconnaissance platform. These guys would go in the day after the big bombing raids and go in and do bomb damage assessment, often flying solo or maybe with one wingman. You can imagine going into occupied territory all by your lonesome. Quite a mission that was done. But again, essentially the same mission with all these. And really something that's well, except for the news chopper, right? That's very different. And I had some other aerial reconnaissance platforms earlier, but had to trim it down. But in the military case, there's something common to all these really is that the reconnaissance is something that was used to inform the highest levels of decision making, right? Historically, it's been something that was used to inform the generals. not necessarily the boots on the ground. And so when we talk about transformational, we're talking about doing a mission that didn't exist before. And so today we have two categories of Aero Reconnaissance platforms that I consider to be very, very transformational. And, you know, if I'd come to you before, and I'll flip back, because if I'd told you when we're looking at this category of aircraft that includes Mach 3 plus and essentially unlimited range and 30 hours of endurance and aero refueling, and the go all the way escort fighter turned into a recon platform, right? And satellites, which obviously have incredible persistence. If you had these concepts in mind when you think about taking pictures from the air, and I told you, oh, what can we do with a 2-pound payload and 30 minutes of endurance, right? A 2-pound payload and 30 minutes of endurance. If you believe that this is aero reconnaissance, you're going to say that's a really crappy aircraft. That is not useful. That is not an aero reconnaissance platform because it doesn't fit in any of these boxes, right? It doesn't do any of these missions. However, right, a 1 or 2 pound payload and 30 and eventually to maybe 90 minutes of endurance is an absolutely transformative capability. And being able to put a reconnaissance platform in the backpack of a soldier in every platoon so that when they're getting shot at, they can find out what's on the other side of that hill, right now. They don't have to go back and talk to the Pentagon and get permission. The pictures that are taken don't cost millions of dollars to take, and they don't then end up in the CIA as classified intelligence, but things that can help somebody boots on the ground right now. That's transformative. And it's not an SR-71 replacement, right? We're not putting U-2 pilots out of business with AeroVironment Ravens. And when we talk transformative, right, AeroVironment sold, you know, something north of 70,000 of them. Okay, we're talking really big markets. We're talking very different things. And the quadcopter there, I was at a wedding not long ago where the bride had a quadcopter videotaping her walking down the aisle, right? I sold and purchased a house recently here in California, and the house that I purchased included aerial photographs taken from a quadcopter in the marketing package. All right? You're not putting News Chopper 6 out of business with a quadcopter taking pictures at someone's wedding, right? This is a different mission. This is something very different. It's very transformative. And I think the last point that I'm going to make here, probably not, but sort of the last point, I think the important thing to think about is what fundamental technology made these transformative vehicles possible, right? What made this happen and it wasn't possible before? And in both cases, it's because they're electric, right? In the case of putting an aircraft in a backpack and being able to deploy it into a war zone, it was really decent batteries and brushless DC motors, autonomy, and those things that go with it, but really electrifying that platform. Those of us who flew model airplanes when we were growing up and remember glow engines fondly cannot imagine taking that into a combat zone, right? That's not a good idea. And likewise, I like to joke about quadcopters because, right, they make the controls problem so easy even a computer science person can do it. It's kind of a lousy aircraft, but the flight dynamics aren't really that anymore, right? But fundamentally what enables them to be done is being able to do it through speed controllers instead of collective and cyclic. So that is something that is inherently electric, as is enabling. And so today when we talk about transformative flight, I think an important thing to think about is we may think about some of these aircraft as being lousy aircraft, right? You may not believe that we can have a useful aircraft with 60 miles range, because what aircraft has 60 miles range, right? Normally today when we take off in an aircraft, we take off from one airport and we fly to another. And for most of us, if it's transport, that's one large international airport to another large international airport. Turns out those aren't 60 miles apart. I mean, I guess you could fly from SFO to Oakland, but we don't normally do that. So, you know, what's really an important thing to keep in mind here is that part of what makes this possible is the very limited scope of the missions. And we've even had interactions with some of our collaborators where people in this community who want to study these kinds of missions and these kind of vehicles, they'll send us a version of their study and they'll say, oh yeah, we did a study just like yours, inspired by what you did at the summit. And we came back and we think you're totally wrong. It needs to be fuel cells. Or they come back and they say, no, you're totally wrong. It's got to be hybrid. You just can't do it with batteries. And we'll say, let's take a look at your study. First thing, boom, they looked at 150-mile range. Like, well, wait a second. Sure, 150-mile range. That's a totally different ballgame, right? Normally in aerospace, you add 100 miles of range to something, and who cares, right? It's 100 miles. It's no big deal. It's a 2,500-mile vehicle. But when you're talking about something that, no, all we need is 60 miles, that's what it is. So I want to spend a little bit of time, and again, I'm still on my diversion, but I wanted to establish, right, how do we know that 60 miles is good enough? Well, part of the answer is we're Uber, and we know where people are and where they want to move within urban environments, and we can use that data. And we can use that data to, and these are all slides, these pictures are slides that I presented at the summit last year. But we can use that data to lay out a network of vertiports. So we can take a city like Dallas-Fort Worth as a metro area, and we understand the demand, and we understand where people are, and we understand where people want to go, and we can use that to arrange the vertiports, right? This isn't just throwing darts up here. This is actually very much based in data and information. And not only do we know from that data where to put the vertiports, we know the frequency with which people want to travel from one to another, right? So we know that dark column there under sort of vertiport I, that would be column number 3, right? That's the big airport, that's DFW. So of course people want to travel there more. And we drop out missions less than 20 miles. But the point is not only do we know where they are, but we know the frequencies with which they want to travel. And you put these two things together and you can create a weighted cumulative distribution function of all the trips. Right, and this is what the trips really look like. This is based on data of how people really want to travel in a real city, right? And turns out 60 miles, we don't need anywhere close to that, right? The average trip is 25 miles, right? You get 99% at about 33.5 miles, okay? You add in headwinds, some route tolerance, some margin for these things, and that's where we get to the 60-mile sizing range. But really what we're looking at is driving this is the ability to keep up an operational tempo of doing these 25-mile missions one after the other after the other. So my point is, right, is when we look at this, for those of you who are convinced absolutely that batteries can't do the job, because let's face it, that's a big question, right? When you're convinced that batteries can't do the job, you're right, they can't go 400 miles. Right, the vehicle doesn't close, it doesn't work. Probably can't go 200 miles, right? Even when you're doing that study and you say, oh, well, we just rounded up, we called it 100 miles. That's not what we're talking about, right? This mission is transformative. It's not replacing a vehicle today. It's doing something entirely different. So, okay, but I was supposed to talk about tools and frameworks. So our tool, our group down there in San Luis Obispo that we're standing up, you may be wondering, and so I'll go into another diversion. You may be wondering, why does Uber need an in-depth engineering team? Why do they need a conceptual design team? Why do we need to do this? And so I think that's the most common question I get out here in the lobby and the hallway, so I thought I'd talk about it a little bit just to address that issue. But really, we play a lot of the roles that anybody who's worked with the government through a procurement process, whether you're on the side of the government or on the side of the contractors, will be familiar with, right? We need to be an informed customer. Fundamentally, that's what it comes down to. We're establishing the requirements. We're setting what is the payload, what is the range, what is the speed. And as we do that, we need to make sure it's possible, right? If I came back and I set those things wrong, then the vehicles don't close and the network doesn't work. And so I need to be able to assess our own requirements with respect to vehicle feasibility. We need to be able to assess the vehicle concepts, both the ones being produced by our partners and also the ones being produced by our competitors. It's just, we need to know what's going on, and that's very much a constructive thing. If we find out that we look at somebody's concept and we come back and we say, this looks great, but we don't understand how you're getting that 0.2 empty weight fraction in order to make this close, maybe we can find out either what miracle technology they've got or what are we missing in the analysis and make sure that we're all moving forward towards success, and that's really our goal. We'll also be proposing some vehicle concepts, things like the CRM-01 model that you've seen presented and that Mark talked about. I really like to talk about that concept as a vehicle for communication, right? It's a non-competitive platform that we can do analysis on, we can potentially do wind tunnel tests, we can share V&V data, and that all the partners, we can exchange this back and forth, and we're not working on one person's concept. And we can have that as an open vehicle for communication. And Uber can put resources and effort into that, and again, try and support the whole community that way. We potentially can do some technology development. Mark highlighted those co-rotating propellers that are in the 001 concept, and he mentioned that we're looking at doing a larger scale test. Really, that test that we're working on is focused a lot on the control system in order to provide that that slight phase shift and maintaining that phase shift between the props very precisely through a wide range of operating conditions. But we're also looking at performance and acoustics of that platform. As well, then, tool development, and what I'm actually supposed to be talking about today is we can look at where are there gaps and where do we think that there's help that's needed. And we can try and then do some of that work and help the community and try and raise all boats. And so I think that if you look at this in terms of the role that NASA or the Army or for fixed wing, the Navy or the Air Force play in aircraft design, it's really a lot of analogous reasons. Right? It's about being a good customer and about supporting the community, because what we want is for our partners to be successful in delivering a vehicle. We've said it a bunch of times, and I'll say it again, right? Uber's not going to make an aircraft. That's not what we're doing. We're trying to help other people make aircraft that we want on our network. So that's really what we're after here. And so specifically, let me talk about some of those gaps that we have identified in the VTOL, the eVTOL tools. And this is not an exhaustive list, and I don't mean to pick on anything. The main thing I want to come in is with frankly, I'll be just very direct. I come into this community with a great deal of humility. Okay, the vertical flight community has worked for very long on very, very hard problems, and there's an incredible amount of knowledge and experience that's amassed in this community. And we're not coming in to this saying that we know better and you've been doing it wrong and right, get out of the way. That's very much not what I'm after here. And so I think you'll see a lot of these things resonate and are familiar. And in certain ways, a lot of what our role will be is to provide glue and grease to a lot of these different things, right? Let's stick things together that currently are separate, and let's lubricate the joints where they're rough and aren't good. And fundamentally, you guys have seen our very ambitious schedule, right? We don't have time to go write codes from scratch, right? We don't have time to go back and do a lot of that. We need everything that this community has done and to build from that, but hopefully in a very constructive way. So the first one there, energetics, mission and point performance. We are planning on using NDARC as the core of our sizing and performance capability. And as Wayne mentioned in his presentation on a couple of days ago, it does have electric capabilities. Some of the component models aren't to the point in the sophistication where we think they need to be. And so that's an example of where we'll work to improve battery models, really working with our battery expert, not just on the discharge side, but on the details of charging, hopefully getting to the point of the details of life and degradation of batteries, as well as some of the very strange behavior of batteries, thermal behavior, even aspects of things like that batteries need to rest, right? They need some time, they need a moment between when you charge them and you turn around and you need to discharge them. And there's, right now, it's not just that the aerospace world isn't capturing these things, it's that the battery modeling community in general is on the fringe of not understanding these things and doesn't really have models. So we'll be doing some pretty fundamental work there that Selena will be leading on our team. And we'll be then trying to pull that in and make it appropriate for conceptual aircraft design. Same kind of thing with electric motor models and other components. I've done some work in electric motor modeling, and I was actually incredibly flattered a few years ago when I saw that Wayne had cited some of my papers and pulled some of those models into NDARC. So that was fabulous. But there's still very much limitations in those, and we need to move them forward. We haven't talked a whole lot about our Flux Optimizer, which is our operations analysis tool that does that kind of thing that we showed about laying out the network in Dallas. But right now, that tool essentially treats the vehicle just as a point, right? It's a point mass that can go any speed, any way you want to. So one of the things that we'll be doing is taking real aircraft performance data and feeding that into our operational analysis, and so that we'll have a heterogeneous fleet of vehicles, and some of them may need to be able to be planned to go around the mountain in LA, and others might go over the mountain. And we'll also be building to the point where we have noise footprints of those vehicles, and we'll be looking at the network and planning those flights and doing the operational analysis, that simulation, taking vehicle performance and noise into account. So we've got to make those connections and feed that, which I think is different than what's available today. The acoustics community has done just incredible work over the years, but the vast majority of it has been focused on late in the life cycle of vehicles. Doing very high fidelity analysis, and they haven't, in the past, they haven't been put up front in the very beginning of the process. And I think that's a failure of programs and industry. That's not a knock on them. That's the situation that other programs have put them in. But so we need to figure out, if we're going to actually walk the walk on making these vehicles quiet, we need to figure out how to get those processes earlier in the process. And I'll talk more about that on the next slide. Part of that, as David Josephson will talk, is about using the right noise metrics, taking in physiology, annoyance, and also background noise in order to come up with what is the right measure and how do we do that. Part of that is designing the propulsor itself to be quiet in the first place, and then also making sure that when it gets integrated onto an aircraft that it remains quiet and that we can provide the most quiet solutions possible. We need the ability to do quick filters on configurations, right? A lot of my team's job isn't going to be to focus on, one particular configuration, say a tandem helicopter, and work on that for 30 years. We're much more in the position of needing to take a dart and throw it at the wheel of fortune and be able to analyze that concept quickly. And then the next day, somebody throws a different dart, and we need to look at that one quickly. And so one of the aspects of this that I think is fundamental is we need very quick ability to assess whether these concepts are able to transition safely and whether they have controllability and what happens to them when they have a failure. And I think that really, if we can do that right, we can separate a lot of the wheat from the chaff in terms of concepts and really filter that down. And of course, the thing that always hurts a conceptual design project is weights, right? It's one of these things. It's a lot harder that we don't always appreciate. And we're headed in a direction outside of our experience and outside of our databases. These vehicles are going to be smaller. They have rotors in different places in different ways, and lots of them, introducing lots of vibration into these systems, and they'll also very likely be composite. And so all of these things that stress our weights models and our knowledge of conceptual design weights tools, so we'll be putting effort in there. And this is not a complete list, but this is to give you an idea of the kinds of things that we are working towards. In terms of acoustics, I have a philosophy of this, that it inherently has to be, for our purposes, a variable fidelity approach. And one aspect of design that's very different than normal engineering analysis is it's not always about using the highest fidelity possible, right? Design, it's very often about the exact opposite. It's about using the lowest fidelity that will answer the question you need, okay? I like to use the phrase, using models that can't be very wrong. Right? That's the level of threshold that you need to make decisions in design. Models that can't be very wrong. They don't have to be 4 sig figs right. They just have to not be very wrong, right? And inherently. So, as a general process, I'm not even putting a design loop or a trade study loop around this, but, we're going to start with geometry and configurations. We need to go to modeling the noise sources, to the propagation, to the acoustic metrics on the end, and then also possibly to the integrated metrics as we fly over a flight path. And I know this is familiar to all of you. This is how it's done. But I want to talk a little bit about our approach and just in general how we're going at it. And I think this will be very familiar to you guys, but I think you'll see the value that Uber will be able to add. In geometry, hey, 3 guesses what we're going to use. Right? Shocker. If you aren't familiar with OpenVSP, go to openvsp.org, give it a try. If you have any questions, I know a guy who can help you with those. So it's really what it's for. It's I'm not going to talk a lot about OpenVSP. That's not what we're here for today. In terms of noise sources, this is really where we have the most branches in our path. First, we're going to need multiple fidelity choices and multiple options for isolated propulsors, and we're looking at things like X-rotor, RCAS, and some other options. What I really want to get to at this point, I'd really like to get to a single tool that can model many of the different kinds of concepts that people are interested in, right? We're talking normal rotors, we're talking normal props. We need to be able to model the stacked co-rotating props. We need to be able to design those stacked co-rotating props. We need to be able to look at props and fans with high solidity, many blades, not just like a blade element that ignores some of those effects. We need to be able to look at non-uniform blade spacing. We need to be able to look at ducted solutions and actually be able to look at the details of the duct, not just sort of hand wave, there's a duct there. We need to be able to do all of those things, and we need to be able to look at non-uniform inflow in those cases. And I think that if you think about, is there a single tool that is at that conceptual design level that can handle all those different kinds of concepts and all those inputs, I think you'd find that it's hard to pick. I think today most of us would end up using half a dozen different tools for that. So that's something we need to go after. And then, of course, on the complete aircraft side, we're looking at, again, a variable fidelity approach. And so we're looking at using CHARM, Overflow, Flight Lab, especially their vortex particle capabilities. Those are all commercially or through NASA off-the-shelf available and trusted tools by this community. We're also doing some things more close to research investment. So OmegaFlow is a tool probably nobody's heard of, but there's a gentleman, there's a team of people who've been doing research, very much research work in vortex particle codes, and we're going to support some of that work to try and push it towards these kinds of tools. And I can talk more about that offline if anybody who's interested in it. But again, what we're really looking at here is bookending the fidelity with established, very well trusted tools that are known, and then also following up that with some more risky plays that would have game-changing capability in terms of being able to rapidly analyze these concepts without having to generate a volume grid and those kinds of things. For propagation, we're really focused on using Ken Brentner's PSU WOP-WOP as the core of that, and we have a big learning curve to come up there, but we think that that's going to be the core tool that we need for that. For the metrics at the end, David Josephson is leading our effort towards establishing the metrics that we need in order to assess these vehicles. Again, we're looking very closely at the ambient noise environment and how the human ear perceives noise and annoyance. There's physiology, and then there's also certification, and pulling all those factors into understanding the noise metrics. And that's sort of for a point observer on the ground. We're also looking at then coupling that with our operational analysis tool and flying flights day and night to integrate that up. And that also factors into certification and understanding what really noise footprint we have. So, and then the loop I've left off of this, right, is any sort of a design loop or a trade study, but we'll be working that too. So that's just an example, and that's the end of my slides. I'd be happy to take questions as I can. Thank you all very much. Professor Schrage.
Endurance and everything, if you have to say hover for 2 to 4 minutes, and you also have to maneuver because the vertiport, you have to go to an alternate vertiport, that seems like that'd have a big impact because the hover, just like on anything else, the hover power is going to tax the battery the most, right?
Sure. So the question, since we didn't get the mic there at the very beginning, was in reference to the study that Professor Brian German and I presented at the summit last spring down in Texas. We had very limited hovers at takeoff and landing, and they were very simple models. It was just to time it at hover power. And what impact does that have on these vehicles? And it's substantial. And I think one of the most interesting things that we found in that study was it's very much configuration dependent, right? Some of the low disk loading, more hover efficient concepts don't pay a huge penalty because they're really good at hovering, And so those concepts can deal with that more, whereas some of the higher disk loading, more cruise efficient concepts, but that have much less hover efficiency, they really are penalized heavily. And so one thing is that some of those concepts are very much looking at doing their transition at the absolute last moment, coming in and staying under wing-borne flight up until you are at the vertiport and you see that it is clear and you are ready to land and come in and do that transition, and spending as little time as possible at hover. So I think that's one way that they're mitigating it. The other thing that we can do to try and mitigate that is knowing the network, right? By understanding when we take off, again, there's lots of benefits of only operating over a known city and over a known environment. One of them is we will know the weather across the city at all these vertiports. And while weather can change quickly, when the flights are typically, about 10 minutes, we shouldn't be surprised by the weather that much. And we will know before we get to a vertiport if there's congestion or if it's fouled, and we'll be able to divert en route because we have that information and we're connected in that way. But in the end, you're right. There's the other thing that we can do, and Tom may mention this, we aren't just setting a single cruise speed for these vehicles. We need the vehicles to be able to cruise efficiently over a range of speeds, plus or minus some range. And the reason is that gives the air traffic team the flexibility to, if you have two vehicles going to a same vertiport, you can tell one of them to fly faster and the other to fly slower, so that they arrive in a deconflicted way rather than they arrive at the same time and one of them has to sit there and loiter or hover for a minute or two. So there's a few answers there, but you're right, it's certainly a part of the challenge. Right up in the front.
So I want to go back to what you were talking about at the beginning, how, okay, you have the data on where people travel, but you have the data on where people travel now. I mean, there's a big piece missing there, which is how can, what are people going to do once you can fly faster and suddenly a 150-mile trip isn't 3 hours, it's half an hour.
Sure.
So you can actually transform the way that people are living, not the way that they are commuting from their current, start and end points. And so I think that really ought to be a piece of the conversation as well. And so it's just a comment on that.
So it absolutely is, and that's called latent demand, and it's really hard to predict. But we're doing the best we can, and because we definitely realize that Uber trips today are not very representative. There's significant limits in that people use Uber for short trips, and it's not as effective for longer trips. So we're also looking at other sources of data that aren't inherently ours, but there are, for example, companies who agglomerate cell phone data and track where people are and where they're traveling, no matter what mode, whether they're walking, driving their own car, taking public transport, or anything else. And so there are sources where you can go out and you can acquire this data that really looks at how are people moving, not just through one mode like Uber, but multimodal across cities. So we're certainly using that kind of information and pulling that in to look at the latent demand. So we're aware, and it's a challenge, but we're headed that way.
Yeah, you talked about day, night, and all weather operations, and it seems like to keep this on a 24-hour operation, you're also going to have the equivalent of what now is like Cat 3B, so that you can have automated coupled approaches and so forth. That seems like a subsystem development to get it to the weights required for these small vehicles to be a big challenge.
So Uber's initial plan is not all weather. I don't think that anybody on our team has mentioned that. I know others have, but Uber will work towards that as the autonomy builds out and in other ways. But our initial approach is day-night, but VFR at the start. And we definitely see that developing that autonomy is a part of the technology arc that we need to go through, and phasing that in and developing data where the autonomy is flying side by side in cooperation with a human pilot. And we do expect to be able to expand operations as we develop those technologies. But initially, when you look at the helicopter service being flown in Manhattan, they pretty much shut down in inclement weather. And their customers are willing to accept that. And we think that initially it's obviously a limitation, but we think it's something we can work with.
All right, in the sake of time, I offer up that Rob will still be here today. You can track him down. You now know what he looks like if you didn't know. And I'd like to thank Rob for his presentation.
Thank you, Mike Chris.